Well, time for us to get going, and we'll start like we often start with a problem. So, given the following, f of x is differentiable between 0 and 7. That means that f is a nice function, the kind of function we'd like to take home to meet our family. And we know the following, that between 0 and 3, not only is it differentiable, but the derivative is not too big. It stays between the values 2 and 5. And then between 3 and 7, it stays between -1 and +3. So the question is, oh, and I guess there's one last thing, f of 0 equals 3. What can we say about f of 7? What's true about that value? Okay. Well, that's interesting. Well, we can probably say that f of 7 exists. It's got to exist. I mean, it's a differentiable function. It's got to be something. But our goal is to say, what could it possibly be? Try to narrow down the range of values we could end up with. So let's start by just focusing right now between 0 and 3, because we do know something about 0. Let's see what we can say about just at 3. So we think about, okay, what tools do we have? Well, the tool we learned last time, it's pretty useful. In fact, some people might say it has a lot of value. It's the mean value theorem. Now, what does that tell us? Well, it tells us that if I look at the average rate of change, f of b minus f of a or b minus a, that's got to be equal to the instantaneous rate of change for some point in between. So my averages somehow line up. My instantaneous average will line up at some point with my average. All right. How do we use this? Well, we say, what do we care about? We're 0 to 3, so I can think of that as being my b and my a. So I can look at f of 3 minus f of 0 over 3 minus 0, and that's got to be equal to f prime of c. Now we know about f of 0, so we can say, okay, what do we have? Well, f of 3 minus 3 divided by 3 has to be equal to the derivative at some point. Now at this point we might say, well, we're kind of stuck, aren't we? But now we have that one other thing that we haven't talked about. We said, hey, we know something about the derivative. So this value on the right-hand side isn't just any number. It's got to be a number between 2 and 5. So this quantity is less than or equal to 5 and greater than or equal to 2. So what do we get? Well, if we clear out the 3, we'll get 6 is less than or equal to f of 3 minus 3 is less than or equal to 15. Or we can say that f of 3 is between 9 and 18. So we can control what's happening. Now what's happening geometrically? Because I think it helps to see the picture. So let's do a quick sketch. So here I am at 0. Let's say this is the value of 3. And what's happening is I say my growth, my rate of growth, is always between 2 and 5. So my slowest possible rate of growth would be if I did a line which had slope 2. My greatest rate of growth would be if I did slope 5. And what's going to happen is that I'm going to always stay in between these two. So my function has to live in between here. Because if I ever went outside of that sort of cone there, I would break that my average rate of growth would not be able to match an instantaneous rate of growth. So that's what happened. And so here at 3, since I went up by slope of 2, well, if I go slope of 2 over by 3, that says I went up by 6. That's why we get 9. If I go up by 5 over by 3, I increase by 15. That's why we got to 18. So we're not done yet, because now we have the second part. We say, okay, that's from 0 to 3. What happens 3 to 7? We got to keep going. So what happens there? Well, what happens there is I don't know exactly where I am, but I can imagine I'm here. And then what's going to happen, if we think of the picture, is we're going to grow either go down by -1 or up by +3. Now my slopes are not quite right, but you can imagine I was a better artist. And that's going to run up until we hit 7. So that would be somewhere in here. But again, I can move this up and down any amount I want. So I could say at the very bottom, worst case scenario, I went by a slope of -1. And at the very top, I went by a slope of 3. So that the possible range of values would be whatever this ends up being. Well, let's see if we can figure that out. So if I went with the slope of -1 from the very bottom, that's worst case scenario. I started at 9, slope of -1 over by 4 units. Where would I end up here? What height? I'd end up at 5, because this is, x change is 4. 4 times -1 is -4. If I went up by 3, where could I possibly end up here? Well, started at 18, went up by 12, so this would be 30. And so, what's going to end up happening is, from 0 to 3, I'm going to move, and then depending upon where I end up at 3, then again, I will continue to expand. And so, we can make a conclusion. You can say, look, f of 7, it's got to be between 5 and 30. So that's a good conclusion. That's a pretty strong conclusion. It turns out we can do a very small, tiny bit better. Could we achieve 5? What do you think? Can we actually make it to 5? If I was going to make it to 5, what would have to be true? Well, what would have to be true is I'd have to hug that bottom line. And I'd have to hug it all the way up, and I'd have to hug it all the way down. But what's the problem? The problem is at 3. If I were trying to hug that bottom line both up and down, I'd have to come together at a sharp corner. Can I be differentiable there? The answer is no. So I can't actually get to 5 because I can't get that sharp turn. But the good news is I can get a turn that's arbitrarily close to 0. Now it turns out arbitrarily close to 0 and 0 are not the same. So the strongest possible result is you can get anything that's between +5 and +30. So be careful about your corners. It's hard to make the corners. All right. So, on to today's topic. So what we're learning about today is we're going to talk about things about increasing and decreasing functions. Now, increasing and decreasing, it's fairly intuitive because we can sort of think about it geometrically. So I say a function is increasing if the values are going up. So if I have a here and here's b, if I look at f of a versus f of b is higher than f of a. I went up. That's what it means to increase. Now decreasing is if I go down. So here's f of a, here's f of b, and I'm going a smaller value. So when we talk about increasing and decreasing functions, we're saying, how does the function change? Am I getting larger values as I move, or am I getting smaller values as I move? All right, so that's the idea. Now, what does this have to do with differentiation? Well, remember that the derivative gives us a lot of information about what's happening locally. So I can look at the derivative and say, okay, if the derivative is positive, then what that means is that near my point C where I took that derivative, it locally is looking like a line with a positive slope. So it's locally going up. So positive derivative means that around C, very close by, I'm moving uphill. If I have a negative derivative, then when I zoom in, then I look like a very flat thing that has a negative slope. Well, that says I'm decreasing, I'm going down. So the information about derivative is one of the easiest ways to figure out whether or not something is increasing or decreasing. So that's why we want to talk about the increasing, decreasing behavior. So, in particular, we have the following. If our function is continuous between a and b, and it's differentiable, then we'll say that our function is increasing between a and b as long as the derivative is always positive, and it's decreasing as long as the derivative is always negative. All right. So that's increasing, decreasing. Now, how do we know when we switch behaviors? So the answer is we take a look and say, well, if our function is a nice function, then the only way I can switch behaviors, that means I have to switch from positive to negative. That could happen when my derivative is either 0, so I'm crossing through like the axis, or if the derivative were somehow undefined. So that's where we look. We say, okay, let's figure out where is the derivative 0, or where is the derivative undefined. You might remember that sounds an awful lot like critical points, because it is. And then we say, okay, that's between those points, we're always going to have a single type of behavior. So increasing or decreasing. Now, this is sometimes referred to in the literature as monotonic, or you might hear monotonicity. Now, if you're thinking of monotonic, you're like, okay, I know these words. Mono, that means one. And tonic, that's like a type of drink. So I need like at least one drink to understand this. But actually, that's not what tonic refers to. So tone is actually referring to sort of a different sense. Sometimes we think of like a musical tone, but you might hear the phrase like, can you read the tone of the room? And so that really means characteristic. So monotonic means that there's a single characteristic. In this case, we care about increasing versus decreasing. So we want to focus on how do we find where things are increasing and decreasing. So it's a very simple process, just a couple steps. First, we find where the derivative is 0 or it's undefined. And we know how to do that. We practice that, and we're going to get even more practice over the course of the next few lectures. Now, once we have these points, we take our number line and we chop it up into intervals. And for each interval, we say, look, each interval, the behavior is the same. It's either going uphill or going downhill. So to figure out what the behavior is, we just pick a point. Any point. And you might say, well, which point's the right point to pick? And the answer is the easiest to work with. Because we like to make our life easy. That's why we're taking calculus, so that things get easier for us. And when we talk about testing a point, we're literally saying, put it into the derivative. We don't care about the number. We care about the sign of the number. Is it positive or is it negative? Because that will tell us increasing or decreasing. And that's what we do in the last step. When we get a positive, we're increasing. Negative, we get it decreasing. And there's a little bit of a note here that says, if I happen to have the case where I have a continuous function and I have the following, I know it's increasing. Let's say, here's my number line. And I turn out that, let's say 3. I know that it's increasing up to 3. And then I know that it's increasing after 3. Well, if it's continuous, I can just say, well, great, let's just eliminate the 3, and we'll just say it's increasing all the way. So that seems like it should be true. And it is, because increasing is really about comparisons. Now, you do have to be careful here. You have to make sure you're continuous. Because some things can happen if you're not continuous. So what's an example? You could have the following. You could have a function that goes up to a certain point, and then has a jump discontinuity, and then goes up again. Now, if you look, am I increasing on that part? Now, you can see it visually. I'm going up. Am I increasing on that part? And again, the answer is yes. But now I ask, is this increasing? And the answer is no, because I can compare. That is certainly bigger than that. But when it's continuous, I'm able to make the comparisons. So I can say, okay, because it's increasing, I can compare myself to 3. Here I can compare myself from 3 to something bigger. So that's what we can do. So let's do some examples. Determine the intervals when the curve y equals x cubed minus 3x squared minus 9x plus 17 is increasing and decreasing. So our procedure, where do we begin? Well, step 1, find where the derivative is 0 or undefined. Well, so let's take the derivative. What's the derivative? 3x squared minus 6x minus 9. Is the derivative ever undefined? No. That's good. That's positive. Good thing to know. Well, so now we want to look at where the derivative is 0. So we say, all right, let's take a look. I have 3. Let's pull out the common term. If I pull that out, I'll get x squared minus 2x minus 3. Well, what would we like to be true? Yeah, it'd be nice if it factors. Does it factor? Okay, good. We're a little bit nervous after last time, but okay, back to factoring. What does it factor as? X minus 3, x plus 1. So, where is the derivative 0? Where are the critical points? At 3 and negative 1. So now, draw the line. That's not a line to divide the problem into 2 parts. This is the number line, and we're going to mark our 2 points, negative 1 and positive 3. So we've split the line into 3 parts. Above 3, between negative 1 and 3, and below negative 1. And now we say, look, for each one of those 3 parts, the function is doing something relatively nice. So we want to understand what's happening there. So let's pick some numbers. Well, again, I just have to pick some number. Let's start in the middle. What's a convenient number between negative 1 and 3? 0. Yeah, you're good at that one. Okay. So to plug 0 into the derivative, and you can plug it into anything that is the derivative, so it's probably pretty easy to plug 0 into there. What do you see? It's negative. So you see that the derivative is negative in that range. Not just at 0, but over the whole range. All right. So let's pick another interval. Let's say below negative 1. What's the number below negative 1? Negative 2. Again, there's not necessarily a wrong answer, because you could say negative 100 or negative 1,000,000. Now 2 is wrong because that's not below negative 1. But, okay, negative 2, I probably will plug it into here. So again, I'm just paying attention to the sign. 3 is positive. Negative 2 times negative 3, is that positive or negative? Negative, because it'll be negative 5. Negative 2 plus 1? Negative. If I multiply all that together, positive times a negative gives me positive. So I can test a point, and I can see that my derivative is positive below negative 1. Last thing, above 3. What's the number above 3? 4? All right. 4. Could pick pi. Pi is above 3. All right. 3. Okay, 4 minus 3 will be 1, which is positive. 4 plus 1 will be 5, which is positive. Now, so the number is 15, but again, we don't care about the number. We care about the sign of the number. And what is the sign? It's positive. So this is great. So, what can we say? Well, where is it increasing? The answer is we look to see where is the derivative positive. So it's increasing up to negative 1 and also above 3. Now this is where me and the book part ways ever so slightly. So the book would write it in the following way, from negative infinity to less than x, less than negative 1, and 3, less than x, less than infinity. I would write it in the following way. You get to include the endpoints. Now you might wonder, which way gives me the points on the exam? Because I'll do it that way. And the answer is, we'll give you points either way. The reason I like to include the endpoints is because when we talk about increasing and decreasing, it's really always about comparisons. So I can't really say that a function is increasing at a single point. What I can say is that a function is increasing when I compare points, or when I look at around a point. And so if I pick any pair of points in this interval from negative infinity up to negative 1, including negative 1, it always has the right inequality. So that's why I like to include negative 1. But, as I said, you'll get credit either way. Where is it decreasing? Yeah, you look for where are you negative? So negative 1 up to positive 3. And again, you could include the endpoints or not, depending upon how you feel. Okay. Well, that's good. Let's do it a couple more times. Another example. Find the largest intervals for which this function is increasing and for which it is decreasing. Now, it's kind of interesting that it chose the words largest as if to imply something was going to happen. Well, what's our procedure? Yeah, we start by taking derivatives. That doesn't change. Okay, so what is g prime of t? 5t to the fourth. Ooh, a quartic. Fun. 20t cubed. Anything else? Minus 60 t squared. All right. So there we go. Well, what can we do to help us work with this? So we definitely can pull out some t's. Lowest power is t squared, so pull out t squared. And everything is a multiple of 5. So we can pull out that as well. All right, so we pull out the 5t squared. And what's left? T squared plus 4 times t minus 12. T squared plus 4t minus 12. Now what do we do? Now we factor it. If it factors, does this factor? Yes. Oh, I love the enthusiasm. Okay, how does it factor? T plus 6, t minus 2, and you can always double check. T squared, that's good. Then you have 6t and minus 2t, that's 4t, that's good, and minus 12. All right. Now we should have said that this is a pretty nice function. So the derivative is never undefined. So now we can look and say, well, where is the derivative of 0? So what's the answer? Negative 6 is 1. What else? 2. 2 is another. Anything else? 0. Okay. So these are our critical points. So now it's more interesting. We don't just have 1 or 2, we have 3. Okay, so we draw our line. Here's our line. We put our points down. We just have to remember what order these numbers go. We'll start with negative 6, start with then 0, and then 2. All right, so now we can go through and test each interval. We can do it in any order. I don't know, let's just go left to right. Suppose I want to pick a number in the leftmost interval. I pick something below negative 6. Any preference? Negative 10. Okay, nice. So we're plugging in negative 10. So we can actually do that computation, g prime of negative 10. Now, the question is, which one is easier to work with? Well, we could take negative 10 to the fourth. It's a number. It's 10,000. So that's 50,000. Then you could subtract another number. Okay, no, let's not do that. Instead, let's use the factored form. Because the factored form helps us see what's happening to the pieces. What are the signs? So let's just go through and read off the signs. The t squared, positive. T plus 6, negative. T minus 2, negative. We put that all together, we get positive. Okay, negative 6 to 0. Pick a point. Negative 1. That's good. Great point. We plug in negative 1. Okay, again, let's do the factored form. Okay, t squared, positive, because that's negative 1. Negative 1 plus 6, positive. Negative 1 minus 2, negative, so negative. All right, 0 to 2. 1. Yeah, that one's kind of hopefully an obvious choice. Okay, t squared? Positive. The t plus 6? Be 1 plus 6 positive. 1 minus 2? Negative. So the result is negative. What? It didn't change. So that's why you always have to check. You can't just be like, I'll just test one, and I'll go back and forth. Because things could stay the same. Okay, above 2. Pi? All right, I'm wearing off on you. Good. All right. So, t squared will be positive. T plus 6 will be positive. T minus 2 will be positive. So the result is positive. So now, the question, what are the largest intervals for which it's increasing, for which it's decreasing? So what you do is you say, okay, so we can see initially it's positive. So are we increasing or decreasing? We're increasing up to what point? Negative 6. So from negative infinity up to, and I like to include negative 6, that we're increasing. Now, by the way, you can also use the interval notation like negative infinity, comma, negative 6 with the square bracket. Okay, now we switch because we're negative. All right, we're decreasing because negative up to where? Up to 2, because we're definitely decreasing from negative 6 to 0, and we're increasing from 0 to 2, and this is a nice function. It's continuous. So we actually get to merge these two together. Again, we can use that sort of 0 in the middle as our glue. So negative 6 up to 2, we're going down. It's going down. Okay, finally, what's the last part? 2 up to infinity. And that's an increasing. Okay, so that's the answer to this one. All right, well, let's do one more. Determine when the function f of x equals e to the negative 4x times x to the 4/5 plus x to the 9/5 is increasing, and when it is decreasing. All right, well, what should we do? Yeah, we probably should do a derivative because that's our process. We say increasing, decreasing. It's simplest to say the derivative. The derivative is storing information about the function, and we can oftentimes get a lot of information very quickly. So we're going to look at the derivative. What rule do we need to take this derivative? Well, we'll probably need the product rule at first. We'll do a little bit of chain rule as well. So let's see what happens. Okay, the derivative of e to the negative 4x. So negative 4, e to the negative 4x. The second term stays as is. X to the 4/5 plus x to the 9/5. Now, add to that e to the negative 4x times, well, the derivative. What's the derivative of x to the 4/5? 4/5 x to the, negative 1/5. Derivative of x to the 9/5? 9/5 x to the 4/5 power. All right. That's not so clear what's going on, but that's okay. We haven't done our wonderful algebra makeover. So we're going to work on it a little bit. What's something we can do to help us get started? Yes, notice how both of these terms have e to the negative 4x. Pull out the common term. So let's start by just doing that. We'll work our way up. We don't have to do everything in one step. That doesn't make us better mathematicians. Sometimes it just makes us riskier mathematicians. Pull out the e to the negative 4x, and I'm going to multiply the negative 4 to these two pieces. So negative 4, x to the 4/5, then minus 4, x to the 9/5. Then here, I pull out the e to the negative 4x, so 4/5, x to the negative 1/5, and 9/5, x to the 4/5. Okay? Now, is there anything we can do? you see anything that we can do? We have a 4x to 4/5. What else do we have? Sorry, negative 4. We have a 9/5 x to 4/5. So what can we do with those two? We can combine them. So if we combine them, what do we get? Well, we'll have the minus 4x to 9/5. Then we have minus 4 and plus 9/5. Well, how do we put those together? Well, we'll need a common denominator. What will be the common denominator? 5. So it's negative 20/5 plus 9/5, which would be negative something fifths. So yeah, 9 subtract 20 is 11. Minus 11/5 x to the 4/5. And now there's a 4/5 x to the minus 1/5. Okay, what's the next thing we can do? Yeah, let's factor out x to negative 1/5. And also let's get rid of our fraction. So let's pull out a 1/5. So we can get rid of fractions. And let's make the leading term positive. So let's factor out a negative. So a little bit of stuff action happening here. So negative 1/5, x to negative 1/5. Pulling all that out, e to the negative 4x. Now, go through term by term. Some of these terms are a little bit easier. The last term is very easy. What's going to be left? It'll be 4. And then because of the sign, it'll become negative 4. Okay, that one's not so bad. How about the middle term? What will be left? The number will be what? Plus 11. And then x to what power? It'll be x to the 1. Because you take 4/5, subtract what you pulled out. 4/5 subtract to negative 1/5 is actually 4/5 plus a fifth. So it'll become plus 11x. Now the first one. Okay, what's the coefficient? It'll be 20. It'll be positive because we pulled the negative sign out. And then when we pulled out a 4, we pulled out the 1/5. There was no fifth to begin with. So you have to increase the top by 5. So that's why you get 20. X to what power? Sorry, what? Second? Okay. So we're up to there. So we get 20x squared plus 11x minus 4. Well, what can we do? Well, what would we like it to do? We'd like it to factor. What do you think? Does it factor? I mean, Well, we're going to go on faith and write stuff down here and think about what could work. So what do we have? Well, we have 4. Not a lot to do with there. That's 1 and 4 and 2 and 2. We've got 20. Oh, there's a lot of choices with 20. You got your 1 and 10. You got your 2 and, 1 and 20, 2 and 10, 4 and 5. So, any thoughts? Well, you can always go quadratic formula. But that seems so not fun. What if we tried this one? Let's see. Because I'm thinking like 11, 16 and 5 can be combined together to make 11. I'd have to subtract the 5 and add the 16 in order to make it work. Does that work? 20x squared plus 16x minus 5x is plus 11x. Wow. That's cool. Factoring continues to be a great tool. Okay. You're a little bit more skeptical though. Now, we're ready to draw our number line. Because now we have a good idea of where our critical points are at. So, where are our critical points at? Let's just go through the terms. E to the negative 4x, is that going to contribute to any critical points? Is it ever undefined? No. Is it ever 0? No. How about that x to negative 1/5? 0. What's the problem? It's undefined because of the negative exponent. But it's still a critical point, so we still include it. How about the negative 1/5? Well, that's never going to make 0. It's always going to be negative 1/5. How about 4x minus 1? 1/4? Okay. We'll put 1/4. How about 5x plus 4? Negative 4/5. All right. So there we go. Well, now we just need to figure out what our signs are. So, let's start maybe here. What's a number bigger than 1/4? 1. Okay, now we check the signs. Negative, because of that term. 1 to the negative 1/5 will be positive or negative? Positive. E to the negative 4, well, the E is nice, it's always positive. 4 minus 1, positive. 5 plus 4, positive. So, there's a negative at the front, but the rest of the terms are positive. And so what's true about this interval? It's negative. Okay, so here we have f prime of x is negative. All right, now, between 0 and 1/4. Yeah. Now the nice thing is, remember, we don't have to know the value, we just have to know the sign. So if you're like, I actually have to evaluate it at an 1/8, I don't. I just have to know enough to figure out the sign. So let's go work through the sign. The negative, we'll make it a negative there. If I take 1/8 to the negative 1/5 power, is that positive or negative? Positive. That's positive. So an 1/8 times 4 is a half. Subtract 1. Negative. That'll be a positive plus 4 is positive. So negative, then positive, positive, negative, positive, and so it is, net result is positive because there were 2 negatives that showed up. Okay, what's the number between 0 and negative 4/5? Negative 1/2. That works. Okay, negative 1/2. Negative? Negative to the negative 1/5 will be negative. If you take an odd root of an odd root of a negative number, it's negative. Positive or negative? Positive. Okay, so that'll be negative 2 minus 1, which is negative. Minus 5/2 plus 4, positive. So we're getting 1, 2, 3 negative terms. So this is negative. All right, something below negative 4/5. Negative 1. Okay, negative, next term will be, next to negative 1/5 will be negative. It's like if you take a cube root of a negative number, it's still negative. If you take a fifth root of a negative number, it's still negative. E to the negative 4x? Positive. Okay, minus 4 minus 1? Negative. Minus 5 plus 4? Negative. So we get 1 negative, 2 negatives, 3 negatives, 4 negatives. Put them together, we get positive. All that negativity canceled out. So that says that we're increasing below negative 4/5. Then from negative 4/5 to 0, we're decreasing. From 0 to 1/4, we're increasing. And then after 1/4, we're decreasing again. So that's the behavior. We're going up and down and up and down. And by the way, we should say that the function, even though the derivative is undefined at 0, the function itself is perfectly okay at 0. Now, what are we going to do with this information? Well, we want to understand what's happening at these critical points. One of the great things about calculus is to say, I want to find the best. In other words, I want to find things which are largest or things which are smallest. So there's some tests which have been developed. There's something called the first derivative test. And this is going to say, let's use information about the first derivative to understand what's the function doing? What's the behavior like? And so what does the test do? Well, the key is in the name of the first derivative test. It uses the word first derivative. So the first derivative tells you information about whether the function is increasing or decreasing. So when we're applying the first derivative test, we're saying, okay, what's the behavior? Is the function going up or going down? And so we look on each side of the critical point and say, tell me about that first derivative. So there's 4 possibilities. So one possibility is that on the right-hand side, I'm positive, and on the left-hand side, I'm negative. Now, if you just think about the picture, you just say, oh, on the right-hand side, I'm positive, which means I'm going up. On the left-hand side, I'm negative, which means I'm going down. If you go up, then down, then you need to be at max. Because on the left, you can see I'm coming up into it. On the right, I'm going down from it. Another thing that could happen is my derivative could be negative on the left-hand side and positive on the right-hand side. So it says you're coming down, but then you're going to go up, which says that the point where you have that critical is a local min. Or you might have it where the derivative doesn't change sign. You might go up and then up, in which case it's not a max or a min. We just say it's neither max nor min. Or it could go down and down. And again, that's what we say, neither. So the first derivative test is to say, look at a critical point, what's happening to the first derivative on either side? Now you might wonder, is there a second derivative test? Well, come back next time. But let's try this out. Let's classify all critical points for the following functions. Now you might think, that's going to take us a while. But we've actually done all the hard work. See, because this y equals x cubed minus 3x squared minus 9x plus 17, we've already talked about the critical points. They're negative 1 and positive 3. So negative 1 and positive 3. Let's look at what the derivatives are saying. The derivative below negative 1 is positive. So what's our function doing? Our derivative is positive, means our function is going up. After negative 1, our derivative is negative. What's our function doing? It's going down. So what's true about negative 1? That's a max. How about at 3? Before 3, we go down, because we're negative. What happens after 3? We go up. So what's true about 3? It's a local min. All right, that's not so bad. All right, how about this next one? T to the 5th plus 5t to the 4th minus 20t cubed minus 31. Now, that one we had critical points at negative 6, 0, and 2. So let's mark those. We got negative 6, 0, 2. So at negative 6, what happens? We're going up, positive, and then we're going down. So what kind of point do we have? It's a max. How about at 0? We're going down, and then we're going down again. So what does that mean? Well, it means that it's having something like this. It keeps going down. It's neither max nor min. So this is a neither. What happens at 2? We go down, and then up, and so 2 is a min. All right, now the last one. F of x equals e to the negative 4x, x to the 4/5, x plus x to the 9/5. Now, here we go. We'll have that for reference. We had 3 critical points, negative 4/5, 0, and 1/4. So let's read it off. I'm increasing, then I'm decreasing. What am I? I'm a max. I'm decreasing, then I'm increasing. What am I? Min. I'm increasing, then I'm decreasing. Max. Going up, then going down. All right. So once you know when things are increasing and decreasing, knowing whether things are max and min are pretty fast. We have a couple minutes. Let's see if we can finish this last one. Find and classify the critical points. H of y equals y plus 1 over y squared plus 8. So take your derivative. What rule do you need? Quotient rule. So you're going to take the bottom times the dirt of the top minus the top times the dirt of the bottom. So if you clean that up, what do you get? Well, you're going to get y squared plus 8 minus 2y squared minus 2y over y squared plus 8 squared. Now, you might be a little bit nervous about the denominator, but you'll notice that the denominator is always going to be positive. So that's a promising thing. That means we don't have to worry about being undefined. Now, if you factor a negative out of the top, you get y squared plus 2y minus 4 over y squared plus minus 8. Does the top factor? Yes? How does it factor? Y plus 4 and minus 2. So where are our critical points at? Negative 4 and positive 2. So here's our critical points, negative 4, positive 2. So let's figure out what's the derivative says. So pick a point between negative 4 and positive 2. 0. So plug it in, negative, positive 4, negative 2. The result? Positive. So here's our little chart for the derivative, f prime. It's positive here. It's a number bigger than 2. 3. There's a negative, then it's positive, and a positive. The downstairs is always positive. So the result is negative. Okay, below negative 4, negative 5, negative, negative, negative. The result is negative. So I'm going down, then up. So negative 4 is what? This is a min. Then I'm going up and then down. So this is a local max. See? That's not so bad. Life is good. And we'll pick up again next time.